Morning everyone. So recall that in the last class we introduced second order linear homogeneous and non-homogeneous differential equation. First we will focus on how to find the general solution of homogeneous second order differential equation. So second order homogeneous differential equation is written as y double dash plus p of x y dash plus q of x y is equal to 0. Following from the previous section, I call it equation 2, whose general solution is represented as yg equal to c1 y1 plus c2 y2, where y1 y2 are two solutions of equation 2. In this section we will see that under what condition c1 y1 plus c2 y2 would be called as the general solution. So we are going to discuss the following result, that yg is a general solution of 2 if and only if y1 and y2 are linearly independent. So linearly independent means one cannot be expressed as a scalar multiple of the other. So remember that whenever I talk of y1 y2, it means I am talking of the solutions of homogeneous differential equation. Yg means the general solution of homogeneous differential equation. So to introduce the concept of LILD, linearly independent and linearly dependent, we will introduce Wronskian, which is denoted as W of y1 y2, where again I am repeating y1 y2 are two solutions of homogeneous differential second order differential equation. So it is expressed as determinant of y1 y2 y1 dash y2 dash, which is same as y1 y2 dash minus y2 y1 dash. So the first result says that y1 y2 is either identically 0 or never 0. Identically 0 means it is 0 at all the values over the interval AB, or it is not 0 at any of the values, which means never 0. So for example, if the interval is 1 to 2, it is not possible that it is 0 at 1.5 and non-zero at 1.6. So this is what we need to be proved. So to prove it, it is already given that y1 y2 are the solutions of the homogeneous differential equation. It means they must satisfy, y1 y2 must satisfy. I am simply writing p and q here, but remember that p and q are the functions of x. So y1 y2 must satisfy the homogeneous differential equations. To simplify, let's multiply equation b by y1 and subtract equation a multiplied by y2. Now try to see that what you are getting. Try to solve it. So if you simplify it, then the first terms in both the equation would gives you y2 double dash and y1 minus y2 y1 double dash. Then p times y1 y2 dash minus y2 y1 dash. There would be two more terms. So yeah, that's it, and there are not more terms, and q y1 y2 minus y1 y2, these two terms are there. So these two terms would cancel out, and that's why this is the required equation. Now let's see how do we solve it further. Can you identify what does this differential equation represent? If you look at it clearly, then you will see that this is simply w equal to 0, and this is w dash, because when you find the w dash, it is y1 y2 double dash minus y2 y1 double dash, and the other two terms would be cancelled out, y1 dash y2 dash. So this becomes a first order linear differential equation, or you can solve it also by variable separable method. So it's a linear differential equation, and therefore its solution is w e raised to the power integration p of x dx is equal to integration q dx plus c, but q is 0 and therefore w is equal to c e raised to the power minus p of x dx. Yes, now two important things. One is the formula. Sometimes it may happen that someone may ask you to find, so it's very important to find the Wronskian for the given differential equation. You may use the approach to compute y1 y2 first and then find the Wronskian, but which is a very longer approach. For the given, if the condition is given, then the Wronskian is very easy to compute using this formula. We will do an exercise over it, so this is very important. The second thing is that why the theorem is proved if we compute w, because it's clear that w is 0 if c is 0, otherwise it's an exponential function, so w never vanishes. Yes, someone may say that, for example, p of x is 1 by x, in that case w becomes cx. So you can say that here c is non-zero, but when x is 0, w is 0. But this condition would not occur, because over the interval p of x, over the defined interval p of x, for example, the interval is -1 to 1. So p of x, which is 1 by x, may not be defined over that interval, because at x is equal to 0 it is not defined. So this would work because we know that for the existence p and q are the continuous. In that case you will see that w vanishes only if c is equal to 0, or it never vanishes. Now let's see a interesting question which says that let y1 y2 are linearly independent solutions of this differential equation. Forget about linear independence right now, just assume that y1 y2 are solutions of this homogeneous differential equation which does not contain 0. Then which one of the following is a possible value for the Wronskian? X minus 1, x minus 2, minus 2, x raised to the power minus 1, 2x plus 1, and none of these. Yes, so the idea is that we do not know how to solve this differential equation. We cannot compute y1 y2, but using this formula we can compute the Wronskian. So Wronskian is c e raised to the power minus p dx. Yes, now what is p? So you have to write down the given equation into the standard form, which is y double dash plus y dash by x minus cos x by x square y is equal to 0. For here you can see that p of x is 1 by x, and therefore w comes out to be c e raised to the power minus log x, which is c by x. Now if c is minus 2, then it matches with option B. So it means that option B is one of the possible solution. Other than that, none of the solution matches to this format. Yes, so you can see that we computed the Wronskian without computing the value of y1 and y2. The next result says that if y1 and y2 are linearly dependent, or y1 y2 are linearly dependent if and only if Wronskian is 0, which also means that if Wronskian is non-zero, then we can say y1 y2 are Li. Wronskian 0 LD, Wronskian non-zero Li. Yes, provided y1 y2 are the solutions of homogeneous second order differential equation. Clear? Now let's see the proof. One side is very simple, so we assume that y1 y2 are LD, which means one can be expressed as a scalar multiple of the other, so y1 is c y2. Now in the formula of the Wronskian, substitute the value of y1 and y2, you will see that it comes out to be 0. The other side is tricky, which says that if Wronskian is 0, then we need to prove y1 y2 are LD. So assume that the Wronskian is 0. Yes, if Wronskian is 0, we will consider the two cases. The first case where y1 is 0, the other case where y1 is not 0. If y1 is 0, then again it is straightforward to say that y1 y2 are LD. Try to think why. take your time and think. If y1 is 0, then why y1 y2 are LD. So if y1 is 0, then y1 can be written as 0 is equal to 0 dot y2. So it can always be expressed as a scalar multiple of y2, where scalar 0 is the scalar, and this means that y1 y2 are LD. So y1, if y1 is 0, it can always be written as 0 y2, and that's why one can be expressed as scalar multiple of the other, and that's why LD. So that means let's consider the case 2 where y is not identically 0. So not identically 0 means there exists a point where y1 is not 0. So let's assume that x0 is the point where y1 is not equal to 0. Now we know that the solutions y1 and y2 are continuous. Okay, it directly follows from the original differential equation where p and q leads, the continuity of p and q leads to the existence of the solution, and these solutions comes out to be continuous. Since y1 is continuous, what does it tell us? So it tells us that there would be a small interval or any interval containing x0 where y1 is non-zero. So it means there exists interval CD containing x0 such that y1 is not equal to 0 for all x belongs to CD. Now y1 is not 0, it means 1 by y1 is defined. Yes, so divide Wronskian, so divide w y1 y2 by y1 square and see what we are getting. So we will get y1 y2 dash minus y2 y1 dash by y1 square, which is y2 by y2 by y1 dash, and which is equal to 0. Yes, because we have assumed that Wronskian is 0, and we have to show that y1 y2 are LD. Now this is 0, which means that y2 by y1 is equal to some constant k for all x belongs to interval CD. Yes, now see that if you consider any point x0 that belongs to CD, it means this point also belongs to AB, and for this point y2 of x0 is k y1 of x0, and y2 dash of x0 is k y1 dash of x0 from this relation. Now let's assume that you have given a second order homogeneous differential equation. Along with that, you have given two conditions at x0. It means the problem becomes an initial value problem. And now recall the existence uniqueness theorem, which says that the initial value problem has a unique solution. So it means that the given differential equation must have the unique solution. Now what does it mean? We have assumed that the given differential equation has two solutions, y1 and y2. Yes, but if it has a unique solution, it means y1 and y2 must be related, which means one must be expressed as a linear combination of the other, or one must be a scalar multiple of the other. So this is an initial value problem having unique solution. Since the solution is unique, therefore y1 y2 cannot be distinct, and therefore y1 y2 must be LD in closed interval AB. And why it's LD in closed interval AB? Because x0 is arbitrary, so it is true for any point that belongs to AB. So x0 is arbitrary. So little bit difficult proof, but once you go through it, things would be clear. But the more important is to remember the result, which says that y1 y2 are LD if and only if Wronskian is 0, which means if Wronskian is non-zero, y1 y2 are Li if and only if Wronskian is non-zero. The next result says that y1 y2 are Li solutions on closed interval AB, then C1 y1 plus C2 y2 is the general solution. So this is the main result which you are looking for, that under what condition C1 y1 plus C2 y2 is the general solution. So the condition is y1 y2 must be Li. Yes. So if y1 y2 are Li, then we have to show that C1 y1 plus C2 y2 is the general solution. Now to show that C1 y1 plus C2 y2 is the general solution, if we assume that y of x is any solution of 2, then there must exist C1 and C2 such that y of x is C1 y1 plus C2 y2, because it's the general solution C1 y1 plus C2 y2. If we have to show that, then it means that any particular solution must be obtained from C1 y1 plus C2 y2. For example, if I put C1 is equal to 1, C2 is equal to 2, and these value must be unique. So that's not important. So if I say that to prove C1 y1 plus C2 y2 is the general solution, we need to show that y of x must be expressed as C1 y1 plus C2 y2, where C1 and C2 are not arbitrary constant now, where C1 C2 is unique. Yes, so we have to show that unique means they must have the value, for example 1 and 5, any value. To show that C1 C2 must be unique, we have one equation. Let's write down one more equation, that y dash is C1 y1 dash plus C2 y2 dash. Yes, so it becomes a system of equation, non-homogeneous linear system of equation. Yes, where we are solving it for C1 C2. Now for solving the C1 C2, it has a unique solution if the determinant is non-zero. So determinant means y1 y2 y1 dash y2 dash is non-zero. Which is non-zero? Because it is given that y1 y2 are Li. Since y1 y2 are Li, and this determinant is the Wronskian, so we know that if y1 y2 are Li, then the Wronskian is non-zero. So since this is non-zero, it means that there exists unique C1 C2 such that y of x is C1 y1 plus C2 y2, which means C1 y1 plus C2 y2 is the general solution. So let's move to the last question of this section. Consider two functions f and g, x cube and x square mod x over the interval minus 1 to 1. Show that w vanishes identically. So let's try to prove it, that why w vanishes identically. So to find the Wronskian, I do not know how to differentiate g dash x. It means I have to consider g of x over the two interval minus 1 to 0 and 0 to 1. And now on both the interval I have to compute the Wronskian. So minus 1 to 0, Wronskian is x cube minus x cube, then 3x square minus 3x square, which is 0. Do it by yourself. Similarly on 0 to 1, Wronskian is x cube, because f of x is x cube in both the case. G of x is minus x cube and x cube, so this is 3x square, which is again 0. So this is part 1. The part 2 says that show that f and g are not LD. So this is not required to show, because over this interval we cannot express one as a scalar multiple of the other. So we can say that f of x cannot be expressed as a scalar multiple of g, cannot be expressed as a scalar multiple of G implies F and G are not LD. Now comes the important observation. The case 1 says that W vanishes identically, which means Wronskian of F and G is 0. The second case says that F and G are Li. Now we just did a theorem that W of y1, y2 is 0 if and only if y1, y2 are LD. But do you think that A and B contradict each other or contradict the lemma which we have discussed? Think over it and you will realize that answer I already gave when I say W y1, y2 are the solutions of second order homogeneous differential equation. Then only that result works. Here I haven't says that F and G are the solutions of second order homogeneous differential equation. So this is just an example to show that y1, y2 are not the solutions of a homogeneous second order differential equation. That result may work, may not work, but it is only defined when y1, y2 are the solutions. And this is why A and B do not contradict lemma 2. Okay, so this is a little bit theoretical section, but it's over. In the next class we will see that how to find yg. Thank you very much.